So our second set of lectures in the hydrosphere is going to be about groundwater. So we have a plethora of groundwater here in Massachusetts due to the geology of the area. So we're going to talk about groundwater, some definitions. So this will be more of a definition-heavy type lecture. And then again, if you have the textbook, this is chapter 12 in the textbook, and then you'll be completing groundwater quiz 1 on Blackboard as you watch this lecture. So the last lecture we were talking about rivers and surface water, so this time we're moving over to groundwater. So if we're looking at, again, the total water on Earth, 97% of that is saltwater, ocean water, 3% is fresh water. And of the 3% of fresh water that we have on Earth, about 30% of that is underground. Groundwater is just as much of a part of the hydrologic cycle as surface water or river water is. So groundwater would be this component down here. Anytime it rains, we get infiltration, water soaks through soil and becomes groundwater. So groundwater is literally just water that's stored below the surface. It's not an underwater river. It's not like an underwater cave or anything like that. It's a little bit less exciting than that. So in most cases, groundwater is just water stuck between rock grains or just in the pore spaces in soil itself. So it's stored below the surface, but again, it's an immense supply of fresh water that we have available to us for use. So just to give you an example, we have a regular house here, and if that house depends on groundwater as their drinking water supply, they're going to have a well, and that well is going to just actively pump water out of the ground, kind of like a straw sucking water out of the ground into the household. But groundwater is stored in underneath the surface in what we call an aquifer, which we'll define in a second. So our blue layer here would be our groundwater. Same thing here. Anytime it rains, that's our blue arrows here. It's indicating rainfall. Water soaks into the ground. And if you have this area that can store and hold water, that is where groundwater is stored. So just to give you kind of an idea of how groundwater works, the same exact way that water flows on Earth's surface through rivers, water will also flow the same underground. The only difference is that water flows faster on the surface because it's interacting with less stuff. There's less friction to slow it down. But groundwater still flows from a high elevation to a low elevation, indicated by these arrows here. It just does it much slower than river water or surface water does. So why should you care about groundwater? Groundwater is 53% of drinking water in the US, or tap water is groundwater. That includes places here in Massachusetts, so you may or may not know that if you're in an area that you think you're on city water, so if you're on city water and you don't have a well at your house, there's a pretty good chance that it could actually be groundwater. So in your city, maybe they pump water out of the ground. Instead of getting it from like a dam or a reservoir, they'll pump it out of the ground and then they will distribute it to your house. So roughly 53% of drinking water in the US is actually groundwater. And then if you drink bottled water, if there are certain specific terms that are written on that bottled water, it could indicate to you that it is groundwater. So it's often that if you have spring water or artesian water, that's two examples, but companies will pump water out of the ground and then put it into a plastic bottle and sell it to you at a huge profit. But it can be groundwater in many cases. So your first question is, I want you to think about what your drinking water source is at your house. Do you know? Do you have tap water that comes from a surface source, or do you have tap water that comes from a well? If you don't know and you're not quite sure, if you have a well, there would be some kind of like object in your yard that has a blue cap to it and a pipe that sticks out of the ground. And then either like in your basement or kind of a storage area, you would have a big blue tank basically that stores your water. So that would be a good indicator that you have a groundwater well. So if we talk about where groundwater resides, there's 70 times more water below the ground than there is above the ground. So there is much, much more groundwater on Earth than there is surface water, as we already discussed. So I think some students often have kind of the notion that groundwater is an underwater river. That can happen, but usually the only place that will happen is in a cave. And most groundwater, again, is just kind of less exciting. It's just in soil and it's just in rock. But this is Mammoth Cave National Park, and this is called River Styx Spring. And it's basically an area where water flows underground, almost like an actual underground river. But what I want to point out is that's more rare. That is the the exception, not the norm, when we're talking about where groundwater is. So when we look at where groundwater is actually stored, groundwater is stored in pores. So if you have a soil or a rock and it has gaps between the individual grains of rock or soil, that's where groundwater is stored. So porosity measures the amount of space in rock, and the more porosity, the more pores, the more gaps that you have, the more water can be stored underground. So if you look at these different diagrams, it basically is comparing the way that you can kind of pack together grains. And the more packed they are, the less water it can hold. The less packed they are, the bigger gaps you can get. More gaps equals more storage space for water, which makes it a much better thing in terms of getting water out of the ground for drinking. So just as an example, if you take a bowl of cereal and you pour milk into it, the milk's going to soak through, fill up the pore spaces until it's full of milk, and then eventually top over the cereal once it's filled up all the space between the cereal. All right, so another property that can be used for groundwater is permeability. So permeability is a little bit different than porosity, but it's just how well water flows through a material. So you can have something that maybe it's gravel versus sand versus silt versus clay. And if water flows through something very quickly, like gravel here as an example, this water might flow through a meter of gravel in 2 minutes. That means it's really permeable. So water flows through it fast, it flows through it easily. As opposed to like sand, it might take 20 minutes. Silt might take 22 hours, or clay could take 2 days. So second question here. So imagine you poured water into each jar. So you got 3 jars here. You got a jar of rice, you have a jar of coffee beans, and you have a jar of flour. So I want you to rank the jars from the highest permeability. Which one does water flow through the fastest? To the lowest permeability, which one does water flow through the slowest? All right, and then feel free to return after you've answered that question. So I have questions back to back here. Question 3 on the quiz. So for each sample above, you have 3 samples, sample A, B, and C. What I want you to do is state if it's high or low permeability, and then state if it's high or low porosity, and then you'll state if it's high or low permeability. Just to give you examples of how quickly or slowly groundwater can flow, if you have gravel, maybe water might move through that gravel about 30 feet a day. That's considered pretty fast for groundwater in terms of it flowing and moving. And then if you have clay, for example, clay doesn't really have water pass through it easily. It more traps water, and then it's kind of stuck there perpetually. Clay might only move about 4 inches per day if you have water moving through clay. So gravel is much better in terms of holding and storing water. So you have a math problem here. This is from the Otis Air Force Base, which is in Massachusetts. There is a known source of groundwater contamination in the Otis Air Force Base. It's basically from the weapons testing that they used to do on the Air Force Base. They dumped all those chemicals into the ground, and it got into groundwater, and then now that contamination is traveling from the Otis Air Force Base to the city of Falmouth, where Woods Hole is. So that's about 3 kilometers apart. That's 3,000 meters. What you need to do is you need to figure out how long it would take for the contaminated water to travel from the Otis Air Force Base 3,000 meters to Falmouth if the water is moving a half meter per day. So just some quick definitions to go through here. We got a couple to go through. So an aquifer is anything that holds groundwater. So if we want to be more sciencey, we're going to say a geologic formation that holds and yields groundwater. All an aquifer is just a rock or soil underground that has holes in it. So if it's got holes in it, it's got pores, it's got gaps, it is a good aquifer because it can hold and store a lot of water. If we have an aquifer basically describes this entire diagram that you have here. There's different layers within an aquifer. So you have what's called the unsaturated zone. So any drop of water that falls as rainfall onto the surface here is going to travel through the soil, through the unsaturated zone, which basically just means that it's full, there's air in the soil still left over, and it will travel deep enough and keep traveling deeper until it crosses into the saturated zone. So in the saturated zone, it's 100% full of water. So every single pore, every single gap that you have is going to be full of water in that zone. So we have unsaturated zone, and it is on top of the saturated zone beneath it. And then in between those two is one more definition, and it's called the water table. So the water table is the imaginary line that goes between the unsaturated zone and the saturated zone. So above the water table, there's air. Below the water table is nothing but water. There's no air left. What I want to say is that the water table can rise and fall, so it's not stationary. So if it's recently rained, the water table will rise. If you're in a drought, the water table will drop. Just to kind of reiterate that concept, if you have a drop of rain that falls on the surface, it will flow through the unsaturated zone. It will travel deeper till it gets into the saturated zone, which is the pores are full of water, and it will cross the water table, which is that imaginary line. If you drill a well, or if your house has a well, basically you can see the height of the water table, and that's usually where the border between the unsaturated zone and the saturated zone is. Beneath that, typically you'll have something called like an aquitard or an aquiclude. These either slow down water or prevent water from going any deeper in the first place. So you'll typically have some kind of impermeable rock. This might be shale. Shale would be a good example. So water can't travel any deeper. It just gets stuck in this porous rock because it won't travel any deeper through this impermeable rock that doesn't hold water. All right, so I mentioned back in the rivers lecture that you can have rivers like the Nashua River that it doesn't go dry year round. And the reason for that is because the river is actually connected to the water table. So the water table goes right through the river in our local area. And what that means is that water from an aquifer will go into a river and make that river have water year round in our local area. So let's talk about what some aquifers look like. They might be made of sand and gravel deposits. So these are just loose piles of sand and gravel. Could be made of sandstone. So sandstone is porous. It can hold a lot of water. Or an aquifer might be made of something like limestone that can have a lot of gaps and pore spaces in it. Okay, so you got 4 maps here. It's showing us sand and gravel aquifers, carbonate aquifers, sandstone aquifers, and then igneous rock aquifers. So your question is based on these maps. What types of aquifers are common in Massachusetts? So our final section here for this lecture is balancing groundwater withdrawals. What I want to point out is that we've got a couple more definitions to go through. If you are adding water to an aquifer, either through rain or snow, that's called recharge. It'd be the same as you plugging in your phone to charge the battery. You're adding power to it. You're recharging aquifer when you're adding water to that aquifer. The other end of the spectrum is discharge. So if you're using your phone, the battery is depleting, it's discharging. You are removing the battery, you're taking the battery, you're taking the energy away. So in an aquifer, we call that discharge as well. And that's removing water from an aquifer. So it can happen naturally, but a way that discharge occurs in an aquifer is usually if you have a well. Think of a well like a straw that's sucking water out of the ground. And if it's taking water out of the ground, it's discharging, it's removing water from an aquifer. So I just said that it can happen naturally. A couple ways that it happens naturally is like the Nashua River, our local rivers around here. If the water table intersects a river, you can have water that flows from underground directly into that river. That's something that we call a gaining stream. You can have caves. So if you have a cave, you can get natural discharge of groundwater. You can have springs, which is where a cave intersects the surface and water comes flowing from underground onto the surface. So that would be a spring. And then you can have wetlands as well. So if you have some kind of layer of water on a hill and it intersects these wetlands, that would be another natural location for discharge of an aquifer. All right, so let me just show you one quick animation, how we can have groundwater go into a river. So just to kind of set this up, we got rainfall occurring. Here is your unsaturated zone. Here is your saturated zone. The water table is in between. And what you'll see is that as water infiltrates, it will feed this kind of low spot over here. All right, so when it rains, we get recharge to the water table. The water table will rise. It will kind of intersect this low spot in this area, and this will play through again. I put it on loop. All right, so rainfall, water infiltrates, it goes into the saturated zone. Water table rises, and then now we get discharge that comes out in this low spot in this landscape. So we're going to finish up with some questions. They're all listed here in tandem, but I'll read them out to you. So question 6 on the quiz, I want you to imagine a scenario in which the amount of recharge in an aquifer equals the amount of discharge. So what will happen to the water table? So will it rise, will it fall, or will it stay the same? Question 7, imagine a scenario in which the amount of recharge is greater than discharge. So will the water table rise or fall, and why? And then question 8, imagine a scenario in which recharge is smaller, less than discharge. So will the water table rise or will the water table fall, and why? So once you've done those 3 questions, I still have a couple more on the next slide to read out for you. Question 9, according to the figure above, how old can groundwater be? And then what is the relationship between the depth below the surface and the age of groundwater? And then final 10th question, define the residence time of groundwater. So if the average residence time of groundwater is 10,000 years, I want you to look up what the residence time of groundwater, what residence time means. And then I tell you that the average residence time of groundwater is 10,000 years. So I want you to reflect on if that surprises you, that groundwater can be 10,000 years old, or does it confirm your prior knowledge of groundwater? Okay, so that was your last question for the quiz, and then you'll have a second lecture as well for groundwater to watch.